This example is a little bit more complex. It requires some power consumption calculation, and it's also more practical. So let's look at the problem together. This op-amp amplifier, it operates with this power supply, and it can do output to no more than 200 milliamp. So the output current will be here. This is the I0, which is no more than 200 milliamp. And we are looking for the maximum gain allowable for the amplifier. So there is another condition that's not given in the problem, which is R1 plus R2 that is equal to 10 kilo ohm. By giving this requirement, it simplifies the calculation, and you will see that as we progress. But in reality, you can give any other requirement, but it doesn't affect the calculation. So again, we are going to use ideal op-amp model for analysis. Okay, step 1, use ideal op-amp model. So we know that V plus that is equal to V minus, and at the same time I plus that is equal to I minus that is equal to 0. So we'll label that down here. And V plus, this is our I plus, and this is node V minus, and this is current I minus. Step 2, I'm going to write the nodal equations. At the non-inverting terminal, we know that V plus that is equal to Vs. At the inverting terminal, we have the current goes into the node from this branch, that is 0 minus V minus divided by R1, plus the current goes in from this branch, which is V0 minus V minus divided by R2. That is equal to the current leaving the node, which is I minus. From this equation, we can start to solve for the gain. From the first equation, we know that V plus is equal to Vs. And in the second equation, we're going to replace V minus by V plus first, then further by Vs. So we have the equation of negative Vs divided by R1 plus Vo minus Vs divided by R2, that is equal to 0. So we can find the gain Vo over Vs, that is equal to 1 plus R2 over R1. So this is the gain that we have. Since Vs is less or equal to 1 volt, and the power supply have a voltage of plus minus 15 volts, from here we can say that 1 plus R2 over R1, that should be less or equal to 15. By giving the condition R1 plus R2 that is equal to 10K, we can further find the range for R1. R1 that is greater or equal to 2 over 3 kilo ohm. At the same time, we had another requirement. So step 4, we're going to deal with the output current requirement. The output current I/O that is composed of the current in these two branches. One branch flow from R2 over R1, then the other is a current going from the load RL. And you might want to know what happened to this branch over here, the current that is equal to 0. So we can say I0 that is equal to the summation of the two currents. The first current that is V0 divided by R1 plus R2. The second part that is V0 over RL. And this has to be less or equal to 200 milliamp. So we can simplify this a little bit. So that it becomes VO, this is 1 over 10 plus 1 over 0.05. This is less than 200. From here, we can get V0 should be less or equal to 9.95, which implies that the gain should be less than or equal to 9.95. So step 5, we can draw the conclusion. From the first part, where we calculated the gain, we only find the constraint that R1 should be greater than a certain number, such that gain that is less or equal to 15. From the second requirement, we find the gain that should be less or equal to 9.95. So in total, we can get the conclusion that the maximum gain should be equal to 9.95.